Welcome to this video on the most important mathematical functions for periodic functions. We've already seen in a previous video that if you want to describe sound mathematically, you will be needing periodic functions. And the most important mathematics functions to do that, to describe periodic functions, are sine, cosine, and tangent. So in this video, we will quickly recap the most important properties of these functions and also some of the special angles for which you should know these functions by heart, which is important if you want to work with them. So let's see a quick outline of this video. So I will be first talking a little bit on periodic functions. And then, as I said, you can build them from sine and cosine. We will look a little bit on special angles for sine and cosine. These functions always come in three, so we have sine, cosine, and then tangent, so also a little bit about that, and some of the standard rules that you should know for those functions. So let's see, first of all, a periodic function in general, sine, cosine, tangent are special examples, but there are more periodic functions, is a function. So a function going from the real numbers to the real numbers is called periodic with period capital T if f applied to x plus t equals f of x. So what does that mean? It means that from 0 to capital T, the function can have any value, but basically then it repeats itself. So if you would graph such a function from 0 up to capital T here, well, I plotted something that is a little bit sine-like. You can plot anything on this interval, so like this, but then it should start repeating itself. So we have this property. If you go capital T further on the horizontal axis, the function is identical to what we had before. What you immediately see from my plot is that if the function is periodic with period capital T, it will also be periodic with period 2 times capital T, 10 times capital T, whatever. So what we in general do is we take the smallest capital T for which the function starts repeating itself. So if a function is periodic with period capital T, it is also periodic with, well, period 2t I wrote here, but in principle some natural number times capital T. So the smallest possible one is called the fundamental period. Officially, what we do in reality is that we say the period and we mean the fundamental period. Examples of such functions are sine and cosine. And the way you can define them is very simple. So you take horizontal axis x, vertical axis y. You take a circle with center at the origin, radius 1. And then if you pick a point on this circle, then its x-coordinate is the cosine, its y-coordinate is the sine. So we have plotted here all points x, y in the plane for which x squared plus y squared equals 1. That's precisely the circle that I drew here. And now if I pick an arbitrary point P here on the circle, I call the angle from OP with the positive x-axis, I call it alpha in radians. Then cosine alpha equals x and sine alpha equals y. That is the full definition, and many of the properties of sine and cosine functions follow from this definition. So you should always have this picture in mind, and it can also help you to derive properties of cosine and sine if you forgot about them. We will be doing that in a second. So first of all, we normally work in radians. That is more convenient for a number of reasons that I won't go into now, but it's easy to convert from degrees to radians. So the principal rule is that pi is 180 degrees. So that means that if you have 90 degrees, that's pi over 2, and so on. And you see here that with 360 degrees, full circle, that equals 2 pi. So it's easy to convert from degrees to radians, and we will be using radians all along. Couple of special angles. If we just start here in this point, then alpha equals 0. and you can immediately read off the cosine and the sine value. It's 1 and 0. If you move 90 degrees, so pi over 2, then you see that the cosine of pi over 2, well, that's 0 because the x-coordinate of this point is 0, the y-coordinate is 1, so the sine of pi over 2 is 1. And we can move 90 degrees further, then we have alpha equals pi in radians, and we can read off that the x-coordinate is minus 1. So we are here. Here is the origin. And the y-coordinate is 0. And then finally, if we move down here, so 270 degrees or 3 pi over 2, we read off that the x-coordinate is 0 because we are located on the y-axis, and the y-coordinate is minus 1. So already some special angles. There are a few more that you should know by heart. And you can easily remember, because if you remember the angle, so 0, pi over 6, pi over 4, pi over 3, and pi over 2, then the sine values are half square root of 0, half square root of 1, half square root of 2, half square root of 3, half square root of 4. And then the cosine values are the same values but read in the other direction. So if you read the sine values here in this direction, then if you put those same values in reverse direction, you have the cosine values. And of course you can simplify this table a little bit because square root of 0 equals 0, so this is just 0. The square root of 1 equals 1, so the sine of pi over 6 is just 1/2. And then here we have a half square root of 4. Square root of 4 is 2, so that just gives a 1 here. So these are the values you should know by heart. If you find this difficult for the final exam, as soon as you can write, as soon as you're allowed to write on your paper, just write down this table or already this one, and then you have these values, you can work with them during the exam. So that is allowed. You cannot have a formula sheet, well, you cannot have your own formula sheet with the exam, but you are allowed to write this down as soon as time starts on your scratch paper, so maybe that is convenient for you. So here is a little animation to show you how you can find the graphs of sine and cosine. Now let me make this full screen and start the animation. And what you will see, I have a point P here on the circle. It starts at x equals 1, y equals 0, so alpha equals 0. And alpha will run up to 2 pi here in radians. So P is going to move along the circle. And while P is moving along the circle, I am going to plot its x and its y coordinates. So let's start the animation here. And you see that P is going to move. And you see that I plot at several points the x and y coordinate. So P is going up to pi over 2, 90 degrees here, which means that the x coordinate is going to 0, the y coordinate is going to plus 1. And what you see is that if P is moving along this circle here, that we get the familiar graphs of the sine and the cosine function. So in red we get the cosine function, in green we get the sine function, and it's just the x and y coordinates as functions of alpha. If you look in the animation, so P is now almost at x is 0, y equals minus 1, and we have almost gone full circle. And when we are there, you will see that the graphs connect. So here you also see that the functions are periodic, and they are periodic with period 2 pi. Okay. So what we have seen in the animation is precisely what I wrote here. That's one of the things we have seen. If you add 2 pi to the argument's alpha, then cosine alpha plus 2 pi is the same as cosine alpha, same for sine. The functions are periodic and the period is 2 pi. What you can also derive immediately from the definition of cosine and sine, the point P was on the unit circle, so x squared plus y squared equals 1, so that gives us that cosine squared plus sine squared is 1. If you make a little drawing, and here the point P has an angle alpha with the positive x-axis, and I also plot Q with the angle minus alpha, then you immediately see in the graph that the x-coordinate, so this distance, of P equals the x-coordinate of Q. So that means that the cosine of minus alpha equals the cosine of alpha. You also see that P, this distance, is the same as this distance, but the y-coordinate has a minus sign, so the sine of minus alpha is minus the sine of alpha. So this follows immediately from a picture. A bit more complicated. If you have the point P here and the angle is again alpha with the horizontal x-axis, if I mirror the point P in the line y equals x, then hopefully you recall from high school, if you mirror in y equals x, the coordinates swap. So the x-coordinate becomes the y-coordinate and the y-coordinate becomes the x-coordinate. So this point Q here, that has an angle of pi over 2 minus alpha, because the full angle, this one, is pi over 2. If I subtract alpha, that's precisely where Q is located. So the x-coordinate of P is a y-coordinate of Q, and the y-coordinate of P is the x-coordinate of Q, and that gives these relations between sine and cosine. Well, we've already seen the graphs here once again. So the cosine function, the x-coordinate, starts at 1 for 0, and then basically it has this shape to 2 pi, and then it starts repeating. The sine function starts at 0, is 1 for pi over 2, 0 again for pi, 0 for, minus 1 for 3 pi over 2, and it's also periodic with period 2 pi. As I already said, these functions always come in 3. So the tangent is the sine over the cosine, and it has this graph here, and the tangent has period pi, not 2 pi, but period pi. Also, if you substitute minus x in the tangent function, you get sine minus x, cosine minus x. We have seen that this thing is minus the sine of x. In the cosine, it doesn't matter. So altogether, you see that the tangent has this property. And it equals 0 if the sine is 0 for x equals k times pi, 0, pi, 2 pi, minus 2 pi, and so on. And it does not exist, it's undefined if we have division by 0, which is if the cosine equals 0, so that's for pi over 2 plus any multiple. And that's what these dashed lines in the graph are, because the function has an asymptote there, a vertical asymptote. Some trigonometric identities that you have probably seen before. I'm not going to prove them, but you can show that you can express the sine of alpha plus beta in terms of sine alpha cosine beta, cosine alpha sine beta, and a similar rule for the cosine. You will get these formulas during the exam on a formula sheet, so you don't have to know them by heart. With these formulas, you can just substitute beta equals minus gamma, and of course then you can use that if you have cosine beta is cosine minus gamma, that is the same as cosine gamma. And similarly, sine beta equals sine minus gamma equals minus sine gamma. Then from these first formulas, you can easily derive the corresponding ones with a minus sign. And finally, if you take in this box here, if you take alpha and beta equal, so you take beta equals alpha, then you see that you get alpha plus alpha, which is 2 alpha. And then here you get sine alpha cosine alpha plus cosine alpha sine alpha. So we have this one that hopefully looks familiar to you. And for the cosine of 2 alpha, we get from this formula cosine squared minus sine squared. And if you use, what I've used here is that cosine squared alpha plus sine squared alpha equals 1. So then you can either kick out cosine squared by replacing it by 1 minus sine squared, or you can kick out the sine by replacing it with 1 minus cosine squared, and then you find this formula and this formula. Then finally, this is all repetition, I'm sure you've seen this before. One of the things that we also use them quite frequently for, sine, cosine, tangent, is if you have a triangle with, on the one hand, an angle alpha, on the other hand, an angle of 90 degrees. So that's indicated by this little block here. That's a 90-degree pi over 2 angle. And then if you label the length of this side as the adjacent side, the length of the adjacent side, this is the opposite side. And then the long side is called the hypotenuse. Then we have these formulas that if you take the sine of alpha, it is the opposite side, the length of the opposite side over the length of the hypotenuse. So sometimes it's abbreviated as OH. For the cosine, we have that you should take the length of the adjacent side over the length of the hypotenuse. And for the tangent, it is the length of the opposite side over the length of the adjacent side. So these are convenient when you have some information in a triangle and you would like to know anything about one of the missing lengths, for instance. So what have we seen in this video? We have seen how you can define sine, cosine, tangent. We have seen some exact values of sine and cosine, and hence also for the tangent, but I didn't show that, for some special angles. And then we have shown some of the properties, and many of them follow from simply looking at the definition as a point on the circle with radius 1. So remember that and make a little picture if you're not sure about how to work with these. That wraps it up for this video. I hope to see you again in the next one. Have a good day.